So this is the ordinary GC property for this homomorphic system for the field applied along the z-axis, and this is magnetic. And one very distinct anomaly is the crossing of these JCH properties, and especially at high temperature, JC at high field is higher at high temperature. This is anomalous. But we confirm that nothing strange in the crystal by measuring this magneto-optical image. Then we try to calculate more by applying an in-plane field. In this case, we have two components. Okay? You see this formula here. This is strange formula, but the exact formula, including JC2 and JC3. Okay? And usually, our sample is in-plane, meaning, and also, so, I told you JC2 is very large, so we speculated there must be very a kind of planar defects along the AD. So one possibility is that when we have, say, stacking ball, like if part of the sample is calcium Fe2 AS2, which can be non-superconductor, then we may have a stronger field. Then we bring the sample to TEM, and what we observe is this kind of defect structure. It's a very dense planar defect, and this is two-dimensional. Along A-axis and along B-axis, we see very similar. And from the top, we see some this circular thing. So this is really a two-dimensional defect in this level of this is very unique defect. And at least at the time of the measurement, we couldn't detect any chemical homogeneity by using this TEM machine, but I will come back to this point in a minute. So coming back to this deep structure of field parallel to the AD plane. So this field state H star is nearly temperature independent. Although JC is increasing like this, so it may suggest that the this H star is maybe determined by geometric factor. And then what is the geometric factor? Which is this defect spacing in the STM image. So H star is roughly 1 tester. If we place 1 tester voltage values, it clearly matches with this defect structure. So we think this first initial increase is a matching effect to this high density defect structure. But the thing is not that simple. Depending on the sample both conditions, most of the time we see this kind of high density planar defects, but maybe 10%, 20% of the sample do not show this kind of planar defects. Instead, they only show this thin, very elongated planar defects. In that case, the JCH anomaly at high field is missing. And also, when we grow the crystal, not in iron arsenic, but in potassium arsenic cracks, we have another defect structure like this. Also, we don't see this anomalous field. Our original TM image, and this is high resolution TM image. Of course, this is exactly the same sample, but different portion. And of course, we should see the same thing, But depending on the observation conditions, it looks a little bit different. Okay. Then we made a very high cut and make an average, and then measure the distance from this line should be always 0.6. However, and when we make a high resolution EDX measurement, actually here potassium is more, and in the same region calcium is less. So it also justifies this potassium 1 to 2 growth interlayer intergroups. Okay. Now this is the cobalt substitution, chemical doping. By replacing iron, part of iron, like cobalt, with electron doping system. So by doing so, TC is going down, and eventually at about 10% of cobalt, TC goes down to zero. But in this region, a small amount of cobalt, when we look in the system, JC originally it showed a very high, strong field dependence. It's now recovered like this. So this is a JC value at low field, zero field, and full Tesla for these things. And as we increase cobalt content, the low field JC doesn't change. The high field JC is strongly enhanced around 5 or 7%. But of course, eventually, since DC goes very low, this JC should go down to zero. Okay, so this is an overview of cobalt concentration dependence, the 3%, 7%, 9%. So as small as 3% cobalt concentration, all these anomalous temperature dependencies go. And okay, then we also try to compare the effect of this cobalt doping with the proton irradiation. And we know proton introduces point. And by irradiating a lot of protons in this normal system, we have a JC enhancement like this. Okay, the highest JC is almost 12.5 megaamps per square centimeter at 2K instead of low field. But when we introduce proton, not that much, but only say a few percent of this, the effect is very similar to cobalt. Once again, this is cobalt. It's pristine and cobalt 3%. Okay? So when we irradiate only 0.1 times 10 to 16 protons, these two are very similar. Okay? So we can conclude that a small amount of cobalt plays very similar role with proton, small amount of proton radiation. Of course, when we do the both, namely cobalt and proton irradiation, we have even higher JC like this. So the comparison is like that. Okay, and in pristine sample, as a function of proton, JC goes up, and by putting cobalt, we have increase of JC, and also in that system by introducing proton, we also have a further increase of JC. Yes. Okay, then now I want to compare here the property of 122 50% potassium group, because the carrier density or carrier density number per iron for this one is the same as the one for phosphate. So we grow this of 50% dot 1 to 2. So this is JC versus H. So let's look at this table. So in the case of 50% dot 1 to 2, of course DC is slightly suppressed, but JC is much more suppressed, less than 1/3. Okay? But in the 1 to 2 case, the alpha is the field exponent, alpha is roughly 0.5 or 0.6, which is very similar to the case of strong field theory predicting. But only in the case of 1144, that alpha number is very strong. Now, what happens? Okay, in this 50% go to 1 to 2, and calcium potassium 1144, we both introduce cobalt in the same amount, 3%, 3%. So in the barium potassium 1 to 2 case, of course, we have an enhancement of JC due to this chemical defect, but the enhancement is monotonic. I mean, this is just the same factor enhancement for each temperature and field. However, in the case of 1144, cobalt, as I told you, remove this anomalous temperature dependence of JC at high field. So that is a specialty in 1144 system. Now I come to the case of heavy ion irradiation in 1144 system. But first, I want to introduce the effect in 1 to 2 systems. So usually we have a columnar defect parallel with each other, and in that case, once we have this kind of double heat formation, so these kinks are easy to move and in some special case, columnar defect may not be very effective. To suppress such a motion of kinks, we can spray the direction of columnar defects like this. By spraying, we can enhance heat. And also spraying can introduce entanglement of policies. So this, of course, there must be some optimal spray angle. And that spray angle was very beautifully experimentally accessed by IBM group. This is a case of YDCO, introduced this is 1G gold, B5 equals leak tester. In this case, this is spray angle as a function, JC as a function of spray angle. JC is the highest around 5 degrees of spray angle. And we wanted to check if the same phenomenon occurs in iron disk. Actually, in this case, we use 1-2 system. Then we have 5 degrees enhancement, similar to this. But when we increase the spray angle from 0, parallel case, 5 degrees, 10, 15, 20, and these are all normalized JC as a function of heat. So we start to see very anomalous peaking, broad peak. Okay. Peak is here is around 2.5%. So in this case, B5 is 8%. So the value of the peak is roughly 1/3. So with all this anomalous peak effect, only occurs in the case of spray columnar defects, CD roughly 20 or 15. Actually, well, this is our image curve showing peak here. But first, YDCO irradiated by Tamegai is very spread, similar to our intentional spread. So I think that this anomalous peak effect here and there occurs at around 1/3 of B5 when the field is applied to the average direction of the spread columnar defects. Then I can say that when we introduce columnar defect, there are two kinds of peak effect. One is this anomalous peak effect, which I just mentioned. The other is the peak effect. This is this peak. This peak is due to self-field effect. So I will explain why we have peak here. Because at zero field, the flux line in the sample should be like this. Due to strong demagnetization effect, the flux lines are strongly curved. So in this situation, the straight columnar defect should not be effective. That's why we have a suppression of JC. That brings this peak at around the self. Okay. Then we explored this anomalous peak effect in various configurations of columnar defect. This is a natural one, the same angle, plus minus. And we can change this angle plus and minus in a different way, or we can change the dose for plus and minus like this. But or we can introduce 3 kinds of columnar defects, this and that, and in the center, or 4 kinds of things like this and red and green. And well, maybe I don't have much time to talk about in detail, but the thing is, when the average direction of the two kinds of columnar defects are away from the C-axis, since we are applying here along the C-axis, this anomalous peak, this purple is the case of CD plus minus 15 symmetric case. The other one, average is now 10 or 20. So this, as we change the average direction to a higher angle, this angle is suppressed significantly. Okay. And then I will skip this. Then we try to see the effect of 3 mode or 4 mode of columnar defect in 1 to 2, once again, still 1 to 2. So here we compare normal case, this bubble, and 3 mode and 4 mode. Okay. So here, obviously, the bubble one shows the most pronounced peak, and 3 mode or 4 mode is suppressed. Although the JC value is higher, but the feature is suppressed. And also, when we go from 10 to 20K, the same peak feature is probably suppressed. Anyway, but well, the presence of third or fourth columnar defect species suggests the peak effect. Then, when we try to see the effect of spread columnar defect in 114 system, our present system, this is our data, JC versus H once again. So in this case, we applied 4 Tesla plus 4 Tesla, total 8 Tesla. Then anomalous peak effect, if it is there, it should appear here, but it is absent. So our interpretation is that although our system has only 2 kinds of columnar defects, this natural planar defect plays the same role as this central columnar defect in the case of 3 mode in 1 to 2. That's why we suppress the anomalous peak effect in 114 system. So I think I don't have much time. Maybe can I use 2 minutes to just introduce?
Yes, you can. Yes, you can, of course.
Okay. Or should I summarize?
No. Please continue.
Okay. Just briefly. So this is a new system, 1144 system. So the structure is kind of similar to 122 or 1144. So it's a stacking of potassium 122 system with a calcium 2F2 insulating. As you can imagine, well, this is insulating barrier, so we would expect larger anisotropy, and the sample is very pretty, and PC is 32K, but the function is very sharp. And as expected, the resistivity transition shows a very strong anisotropy. H power to AB shows a sharp transition, while H power to C is broad. And resistivity also supports that kind of anisotropy. But what this is a hysteresis for H power to C axis. The JC value without any defects in this system is very large. This is one of the largest JC in the pristine ungrown sample. And of course, we speculated something strange can be happening in the sample, but our magneto-optical imaging once again shows the sample is very homogeneous, except for this small flux here. But then, what could be the origin? This is, as I showed you, the defect structure in 1144. But in the case of 12442, although JC is very high, we don't have any visible defects seen from the A-axis. Maybe the defect is much smaller, atomic size in this case. And of course, we inspect in the case of H power to AB, but in this case, H power to the AB JC is smaller than H power to C JC in contrast to 1144 system. Okay, so I think that's it. So let me just summarize. I have introduced 1144 systems. This is a derivative 1 to 2. And JC value is not very much special, especially large, but we have a lot of various kinds of planar defect structures, and it shows a very strange JC temperature dependence at high field. And we, at least, one of the high density planar defects are potassium 122 interpose. And due to this defect structure, JC for H power to AB is very large. And we confirmed cobalt doping and also proton radiation enhances JC very much. And also I introduced this anomalous peak effect, which occurs around 1/3 of D5 when we spread around the defect. However, this anomalous peak effect is absent in 1144, which is probably due to this high density of defect. And finally, I just introduced this 1242 system, which has the highest JC among all the ion system. Thank you very much.
Thank you.
Thank you very much for 1144 and also the quite recent samples 12442. So, there any questions or comments from the audience and also from the people from attending the Zoom? Okay, I have a question. for the 1144, there are several potassium 1 to 2 layers is present. What about the stability of the samples? If you expose to the air, I expect some degradations of the samples.
Well, actually, the sample are very stable. We don't see any degradation. Actually, I showed you two kinds of TEM image. Initial one and later high resolution one. In between, we could the last one was measured 1 year after. Okay, and in that period, defect structure didn't change at all, and also JC value was almost the same. So it is very stable.
Okay. And also the second question is about, you mentioned that the matching field effect for 1144 samples.
Mm-hmm.
And do you also observe the matching field effect for the irreversibility line?
We haven't explored because, well, matching effect only occurs when we apply the field in the plane. And this is a special situation, and we didn't try to measure up to very high temperatures because for that we need to measure high temperature. We didn't do that.
Okay. So any question? Okay. One question from the Aki, please.
Professor Tamegai, thank you very much for the very nice talk. We enjoyed pretty much. So one thing I would like to ask you is that maybe this is quite a basic question, but is the calcium potassium 1144 is best choice, or if the combination of elements changes, the superconducting properties of 1144 system changes significantly?
Well, actually, we have tried to grow strontium analog, in this case, strontium rubidium, but actually we failed. Now, as I told you, people have succeeded in growing European rubidium case. The chemistry of European rubidium should be very similar to strontium rubidium, but we failed to grow. So, of course, European rubidium 1144 is very interesting in its own right from its magnetic properties for competition with superconductivity. But I think the non-magnetic one would be more interesting if you try to compare the superconducting properties with calcium potassium. But unfortunately, we have not succeeded in growing other non